Hello there. Welcome to the Sleepless Curiosity, where your imagination can wander freely, even as your body rests. Tonight, I want to take you somewhere you've never been, not out among the stars, but inward into the smallest chambers of your own mind. Here's the question: could your thoughts be more than sparks of biology? Could your brain, in its silence, be entangled with the very fabric of the universe? As you drift here with me, tell me, where are you listening from? What hour has found you? The comments below are always a quiet gathering, a constellation of time zones. And while you're here, don't forget to leave a like, to subscribe, so that these bedtime voyages continue to live. Because what you're about to hear is a story so strange, so unlikely, that it blurs the line between science and dream. Yet it is real, and the fact that you are listening now means you already carry its mystery inside you. Close your eyes. Let the night open. We are about to step into the secret storm where mind and cosmos might touch. Prepare for a journey into quantum consciousness beyond comprehension. We begin. Beneath the surface of every waking moment, beneath the rise and fall of breath, there lingers a question so old that philosophers could only circle it with poetry. What is it to be aware? You can feel the texture of your own thoughts, the glow of sensation, the quiet certainty that you are more than the sum of firing neurons. And yet science, with all its equations and microscopes, struggles to account for this shimmering presence we call consciousness. This dilemma is known as the hard problem. It is not about how the eyes detect light or how neurons signal with chemistry. That is the easy part, the machinery. The hard problem is why those signals do not pass in silence. Why do they gather into a first-person world, a space of color, sound, memory, and meaning? Why is there a you at the center of all this motion? In the late 20th century, one man dared to suggest that the answer might lie far below the scale of neurons, far deeper than synapses firing across chemical gaps. Roger Penrose, a mathematician who gazed at the foundations of reality, proposed that consciousness could not be explained by classical physics. To him, awareness seemed too precise, too non-algorithmic, too rooted in something beneath the ordinary flow of biology. He wondered if the spark of mind might reside in the very strangeness of quantum mechanics itself. Quantum mechanics, that delicate fabric of probabilities, tells us that a particle can live in a state of maybes until observed, when the wave collapses into a single reality. Penrose suggested that this collapse was not merely a mathematical trick, but a physical event, one that could be tied to the emergence of consciousness. The idea was radical, and it broke the symmetry of neuroscience. Instead of thought arising only from vast webs of neurons, it suggested thought could flicker from within the quantum shadows of matter itself, aging your awareness not as the hum of circuits, but as the flicker of a candle flame hidden inside the atom. Imagine the act of observing the world, of seeing this very moment as something born from the collapse of a quantum possibility into a singular now. The audacity of this vision stunned many and inspired a handful to follow its light. Skeptics quickly gathered. They argued that brains are too hot, too noisy, too wet for quantum effects to last more than a trillionth of a second. To them, Penrose was building a castle of thought on grains of shifting sand. And yet, even as objections rose, the question refused to die. Could it be that the most mysterious property of the universe, our awareness, was linked to the most mysterious science ever discovered? Science thrives in these fractures, where certainty fails. Some call consciousness the final frontier of biology. Others claim it is the most fundamental property of reality, waiting for physics to catch up. Whether skeptic or dreamer, all agree the spark of mystery burns too brightly to ignore. Here we stand at the threshold, a question pulsing through neurons, whispered by atoms, written across centuries of thought. Is your mind merely matter, or is it the place where matter itself becomes more than what it seems? The journey has begun, and the darkness ahead carries both peril and wonder. Close your eyes for a moment and picture the vast gulf between numbers and awareness. A calculation unfolds on paper with strict precision, yet the act of seeing it, of understanding what the symbols mean, belongs to a realm beyond arithmetic. For Roger Penrose, the English mathematician whose mind wandered between geometry and philosophy, this gap became the seed of a daring claim that consciousness cannot be explained by algorithms alone. Something deeper, stranger, must be hiding beneath thought. In 1989, Penrose published The Emperor's New Mind, a book that rippled through the scientific community like an earthquake. In its pages, he argued that the human mind could not simply be the output of computational processes running on the wet hardware of the brain. To him, mathematical insight, the sudden flash of intuition, the ability to grasp truths not reducible to mechanical steps, these were evidence that the mind was not just a biological computer. He suggested that hidden within the fabric of physics, there must be non-algorithmic processes, and that the key to them lay in the mystery of quantum mechanics. Quantum theory had already been called the strangest triumph of physics. Electrons slip between possibilities, photons interfere with themselves, and particles separated by vast distances seem to share a single hidden thread. The mathematics predicts the probabilities with unrivaled accuracy, but the meaning, what actually happens, remains an enigma. Penrose believed that somewhere in this space between the possible and the actual lay the missing ingredient for consciousness. He went further, offering a hypothesis called objective reduction. The idea was bold, that the collapse of the quantum wave function, the moment a probability condenses into reality, was not random or merely due to observation. Instead, collapse occurred when the difference between possible states of matter grew too great to remain suspended. At that threshold, reality made a choice, and Penrose argued that this fundamental, irreversible act, the cutting of possibility into actuality, could be the spark that generates consciousness. Imagine each moment of awareness as the universe choosing between multiple paths, each path a delicate branching of probability. When you decide to lift your hand or to follow a thought, perhaps beneath that choice lies not only the shuffling of neurons, but a collapse, a microscopic flicker of the cosmos resolving itself into one version of events. Awareness in this vision is not an after effect of biology. It is entwined with the fabric of existence itself. Penrose's proposal ignited both fascination and outrage. For many neuroscientists, the claim seemed reckless. Why invoke the uncertainties of quantum physics when so much about the brain remained unexplored? They accused him of reaching for mystery to explain mystery. Consciousness was already slippery. Why drape it in the shadows of an even stranger science? And yet, Penrose did not walk this road alone. In the 1990s, he met Stuart Hameroff, an anesthesiologist who had long puzzled over how general anesthesia could erase consciousness while leaving much of brain activity intact. Hameroff had focused his attention on microtubules, tiny cylindrical structures forming the scaffolding within neurons. These microscopic tubes, only nanometers wide, seemed to play roles not only in shape and transport, but possibly in organizing electrical activity. To Hameroff, they looked like ideal candidates for quantum processes, structures that might host delicate vibrations and entanglements shielded from the noise of biology. Together, Penrose and Hameroff forged the theory of orchestrated objective reduction, or OR. In their vision, microtubules inside neurons could act as quantum computers, hosting fleeting superpositions of states. When these states collapsed according to Penrose's objective reduction, the event was not random, but infused with the weight of consciousness. The orchestration came from the biological system itself, guiding these collapses into the patterns we experience as thought, awareness, and self. The implications were breathtaking. If true, it would mean that your very sense of I am arises not from the classical firing of synapses alone, but from orchestrated dances of quantum events within the hidden architecture of your brain. It would mean that every flicker of thought is entangled with the deep rules of reality, rules that lie beneath computation, beneath logic, beneath algorithm. Critics, however, were unsparing. Physicist Max Tegmark calculated the decoherence times in the brain, the timescales on which quantum states would lose coherence due to interaction with their environment. His result was devastating, fractions of a trillionth of a second. In his view, any quantum superposition within neurons would be destroyed almost instantly in the warm, noisy environment of living tissue. To imagine otherwise was, he said, like expecting a sandcastle to survive in a hurricane. And yet, history has a way of humbling certainty. For years, it was assumed that biology had no use for quantum mechanics. But then, research in the early 2000s revealed evidence of quantum coherence in photosynthesis. Plants, algae, even some bacteria seem to guide energy with quantum efficiency, allowing excitations to explore multiple pathways at once before collapsing into the most efficient route. Suddenly, the line between physics and life blurred. If plants could sustain quantum coherence in their cells, could neurons find a way as well? The debate sharpened. To skeptics, OR was still speculation perched on fragile evidence. To supporters, it was a daring map pointing to experiments that might transform our understanding of mind. Even Penrose admitted the theory was incomplete, a first attempt to weave together the threads of mathematics, physics, and consciousness. But like a seed carried by wind, the idea found fertile ground in unexpected places, from quantum biology to artificial intelligence, from anesthesiology to philosophy of mind. The impossible idea had entered the conversation, and it would not leave. Whether true or false, it forced scientists to ask questions they had long avoided. Could consciousness truly be explained in classical terms? Or had we overlooked a realm where thought itself rides on the quantum waves of existence? The journey moves forward, but the echo of Penrose's claim still lingers. In every neuron, in every microsecond of awareness, there may be a flicker, a threshold, a decision written into the laws of physics themselves. If so, then each moment of your life is not only biology in motion, it is the universe collapsing into the story of you. Imagine descending into the architecture of your own brain, not at the level of neurons glowing in a scanner, but deeper, down to the microscopic skeletons that hold each cell in shape. Within every neuron lies a lattice of filaments, highways of transport, and structures so small that 1,000 of them could fit across the width of a human hair. Among these intricate elements, one stands out: the microtubule. Microtubules are hollow cylinders built of repeating proteins called tubulin. They stretch and bend, assemble and disassemble, endlessly reshaping the cell's interior. At first glance, their role seems humble. scaffolding for the neuron's form, railways along which molecular motors haul nutrients and neurotransmitters. They are the hidden beams and girders of the brain's cathedral, unnoticed but essential. Yet, to Stuart Hameroff, they were not just scaffolds. They were candidates for something far stranger, tiny chambers where the rules of quantum physics might shimmer beneath the flow of thought. Hameroff's fascination began with a simple mystery: why anesthetics work. For over a century, doctors have used gases like ether, halothane, and xenon to slip patients into unconsciousness. These substances do not destroy neurons. They do not paralyze synapses or halt electricity in the brain. Instead, they switch off the very experience of awareness, leaving memory and sensation gone, yet the machinery of the brain still humming. Where then does anesthesia act? Hameroff believed the answer lay in the microtubules. Each tubulin protein has aromatic rings, molecular structures where electrons swirl in clouds. These rings can, in principle, host quantum vibrations. Hameroff proposed that when bundled together in the repeating lattice of the microtubule, these proteins might synchronize, creating extended patterns of quantum coherence. In this vision, microtubules are not static supports but resonant instruments capable of humming with hidden harmonics. Penrose and Hameroff together imagined these microtubules functioning like quantum processors. Instead of ones and zeros, they could hold delicate superpositions, patterns of maybes spread across the lattice. Billions of such lattices exist in your neurons, and if they were coupled, they could weave immense networks of information processing. When these quantum states collapsed, Penrose's objective reduction, they might crystallize into the very moment of conscious experience. Awareness, then, would not float above the brain, but arise from orchestrated events inside its cellular bones. It is a vision that feels like science fiction, a brain within the brain, a hidden orchestra playing in the nanoscale shadows. To skeptics, it sounds implausible. Warm, wet cells are hostile to quantum states, they argue. Decoherence, the collapse of superpositions due to environmental disturbance, should destroy these patterns almost instantly. Tegmark's calculations predicted coherence times measured in femtoseconds, vanishing before a neuron could even twitch. The brain, he said, is far too noisy for quantum order. But Hameroff and Penrose countered that nature is full of surprises. Just as certain crystals shield delicate vibrations, perhaps microtubules had evolved to protect coherence. Their hollow, cylindrical shape might act as resonant cavities. Networks of tubulin proteins could form error-correcting structures, reinforcing quantum patterns. And deep within neurons, where energy landscapes shift and flows of ions create rhythm, maybe there exists a sanctuary where quantum order can linger longer than theory predicts. Evidence remains debated, yet tantalizing. Some laboratory studies have reported oscillations in microtubules at frequencies suggesting coherence. At room temperature, under certain conditions, researchers have claimed to detect collective vibrations spanning large sections of tubulin lattices. Are these echoes of quantum processes, or are they artifacts, illusions born of complex but classical chemistry? The answer is uncertain, yet even uncertainty keeps the idea alive, refusing to let it fade into silence. The appeal of microtubules lies not only in their structure, but in their scale. A neuron's synapse measures tens of nanometers, but a microtubule lattice can extend for micrometers within a single cell, orders of magnitude larger, bridging quantum with biology. If coherence were sustained there, it could influence the firing of neurons, nudging networks of thought. In this way, the microscopic could touch the macroscopic, the quantum flicker could guide the mind's thunder. Picture it, deep in your cortex, beneath the electrical storms that EEGs measure, beneath the neurotransmitters swimming across synapses, billions of tiny cylinders hum, each one a pipe in an unseen organ tuned by evolution, whispering with vibrations no instrument has yet fully captured. The music is fragile, drowned easily by noise, yet it may carry the rhythm of awareness itself. Still, doubt lingers. Perhaps microtubules are only scaffolding, nothing more. Perhaps consciousness does not need hidden order. Yet, even skeptics admit, the mystery of anesthesia demands an answer. The silencing of awareness with molecules as simple as xenon cannot be brushed aside. And if those molecules bind not to synapses, but to tubulin, the case for microtubules grows stronger. In the end, microtubules are more than cellular beams. They are symbols of possibility, points where imagination and experiment meet. Whether they truly host quantum computation or not, they remind us that the brain is deeper than we think, its architecture layered with secrets still unfolding. To follow those secrets is to walk into the heart of mystery, where physics and biology blur, and where the hidden order of consciousness may yet be revealed. Step closer to the heart of the debate, and you feel the storm gathering. It is not the soft hum of speculation, but the roar of physics itself, challenging the idea that delicate quantum whispers could survive inside a brain of heat and water. To many scientists, the claim that consciousness is quantum is not only extraordinary, it is impossible. The objection begins with a single word: decoherence. In the world of quantum mechanics, particles can exist in superpositions, living in several possible states at once, until interaction with the environment forces them to collapse into one reality. But these states are fragile, destroyed the instant they interact with stray photons, random vibrations, or heat. In the ultra-cold vacuum of a laboratory, physicists struggle to preserve coherence for microseconds or milliseconds. How then, they ask, could a living brain, soaked in fluid at 37 degrees Celsius, buzzing with electrical chaos, shelter such fragile phenomena? Max Tegmark, a physicist known for his bold visions of cosmology, took up the challenge in the 1990s. He calculated how long a quantum state could last inside a neuron before decohering. His result was merciless. Coherence times measured in femtoseconds, quadrillionths of a second. By comparison, the timescales of neural firing are measured in milliseconds, 1 trillion times longer. To believe that quantum processes could influence consciousness, Tegmark argued, was like believing a snowflake could survive in a furnace. His analogy struck home. In lecture halls and journals, the image of a sand castle in a hurricane became shorthand for why the OR theory could never work. The brain, warm and wet, was the worst possible place to look for quantum coherence. Decoherence was too fast, too brutal, too unforgiving. And yet science thrives on such clashes. For every objection, a counterpoint arises. Hamer, Off, and Penrose countered that Tegmark's model was too simplistic, treating microtubules as if they were isolated particles rather than structured lattices. They suggested that nature might have evolved protective mechanisms, shielding coherence the way a pearl shelters its core. Still, the skepticism was fierce. Physicists reminded the community that laboratories spend billions creating environments shielded from every whisper of noise just to hold quantum states for microseconds. If such extreme conditions are required, how could evolution have conjured the same miracle within a cell? To them, invoking quantum mechanics to explain consciousness was not science, but a retreat into mystery. But here lies the paradox. Biology often achieves what physics deems improbable. Consider photosynthesis. For decades, scientists believed plants simply used classical chemistry to shuttle energy. Yet in the 2000s, experiments revealed fleeting coherence guiding excitations across molecules, quantum pathways persisting in warm, messy cells. The hurricane, it turned out, was not absolute. Under the right structures, the storm could be navigated. The objection remains: is the brain such a structure? Most neuroscientists lean toward no. They argue that classical explanations are not only sufficient, but already successful. The firing of neurons, the synchronization of oscillations, the integration of signals across networks, all of this can be modeled without quantum physics. Consciousness, they insist, may be strange, but it does not require rewriting physics. And yet, even the fiercest skeptics admit something humbling. We do not fully understand why consciousness exists at all. Classical models explain correlations between neural activity and awareness, but the bridge from activity to subjective experience, the feel of red, the taste of memory, remains unbuilt. This gap, the hard problem, is what keeps the quantum idea alive. So the hurricane objection is both a warning and a challenge. It reminds us that coherence is fragile, that claims must withstand the scrutiny of physics. But it also asks us not to underestimate nature. If evolution can shape wings from bone and air, eyes from darkness and nerve, perhaps it can also carve out hidden sanctuaries for quantum order. Imagine standing in the middle of that storm, heat swirling, ions rushing, neurons firing in billions of sparks. Within this hurricane, is there truly no shelter? Or has life, across eons, found a way to protect delicate structures, weaving order out of chaos? The truth is not yet known. Decoherence may indeed shatter every superposition before it can matter. Or perhaps microtubules, proteins, and cellular rhythms create islands of calm, moments where probability can linger just long enough to shape the mind. The storm rages on in journals and conferences with calculations, countercalculations, experiments, and rebuttals. The hurricane objection remains the strongest wall against quantum consciousness. Yet walls can sometimes conceal hidden doors. The next step in the journey will take us beyond argument and into evidence, into the strange ways life already uses quantum mechanics to survive, suggesting that even hurricanes can be weathered. Step away for a moment from the human brain and peer instead into the broader theater of life, across the green surfaces of leaves, inside the eyes of migratory birds, even within the enzymes that fuel our cells. Nature appears to have discovered a secret, that the strangeness of quantum mechanics can be not a hindrance, but a gift. These discoveries are the bridges, the hints that perhaps the hurricane of biology is not so hostile after all. Begin with something deceptively simple: sunlight falling on a leaf. For centuries, photosynthesis was thought to be a straightforward process. Light excites an electron, and that electron hops from molecule to molecule until it reaches the reaction center where energy is stored. Classical chemistry seemed sufficient to explain the journey, but in 2007, researchers probing photosynthetic complexes with ultra-fast lasers discovered something astonishing. The excitations were not stumbling along random paths. They were exploring many paths simultaneously, as if the energy were a wave spreading across the molecular network. This was quantum coherence, persisting for hundreds of femtoseconds, guiding the excitation to its most efficient route. Think of it this way: a traveler facing a forest of tangled roads could stumble blindly, trying one path after another, wasting time and energy. But quantum mechanics allows the traveler to walk all roads at once, to feel the contours of possibility, and then collapse into the best choice. Plants, bacteria, and algae were quietly performing a kind of quantum computation every time they captured sunlight, an elegant efficiency machine hidden in plain sight. The discovery shook assumptions. If fragile quantum states could persist in the wet, warm chaos of a leaf, then perhaps the hurricane objection was not as absolute as once thought. Life had found a way to stabilize coherence long enough to matter air, and if plants could do it, why not brains? The evidence did not stop there. Consider the robin, a small bird capable of migrating thousands of kilometers, navigating not only by stars and landmarks, but by the Earth's magnetic field. For decades, the mechanism of this magnetic sense was elusive. Then came the radical idea that it might depend on quantum entanglement. Within the bird's eye, molecules called cryptochromes absorb photons, creating pairs of electrons whose spins are entangled. The orientation of these spins is exquisitely sensitive to magnetic fields, altering the chemical reactions and allowing the bird, in effect, to see Earth's magnetic lines. Entanglement, an effect Einstein once dismissed as spooky action at a distance, was guiding the flight of migratory birds. Or look even closer, into the machinery of enzymes. Some reactions in the body happen far faster than classical models predict. In many cases, the secret lies in quantum tunneling. Instead of climbing over energy barriers, particles slip through them as if passing through a ghostly wall. This tunneling allows enzymes to accelerate reactions by factors of millions, sustaining life at speeds classical chemistry cannot explain. Without quantum tunneling, metabolism itself would crawl to a halt. Even the sense of smell may bear quantum fingerprints. One theory suggests that receptors in the nose do not merely recognize molecules by shape, but by their vibrational spectra. Electrons might tunnel across odorant molecules, sensitive to quantum vibrations, giving scent its extraordinary specificity. While this theory remains contested, it is another glimpse of quantum possibilities woven into biology. Each of these examples reveals a pattern. Life is not a passive victim of quantum fragility. It is an active architect, shaping molecules and structures to shelter coherence, to use entanglement, to exploit tunneling. Where physics warns of hurricanes, evolution has built shelters. Skeptics respond with caution. They agree that quantum effects appear in biology, but emphasize that most are fleeting, specialized, and limited to molecular scales. Photosynthesis, bird navigation, enzyme catalysis. Yes, they are real, but they do not prove that the brain's complexity requires quantum explanation. To leap from leaves to neurons, they argue, is to stretch the evidence too thin. And yet, the metaphor is compelling. If evolution discovered ways to channel quantum mechanics in leaves, wings, and enzymes, could it not also do so in microtubules? Might the brain, the most intricate organ evolution ever sculpted, be the stage for quantum choreography more elaborate than any leaf or bird? Picture it, coherence flickering not only in the chloroplast of a plant cell, but deep in the cortex of your mind. Entanglement, not only in a robin's eye, but across networks of tubulin. Tunneling not only in enzymes, but across the tiny landscapes of neurons. Life's quantum tricks are not proof, but they are whispers, telling us that the boundaries between biology and physics are porous, and that consciousness may yet dwell in that porous space. For those who seek the quantum mind, these discoveries are inspiration. They prove that coherence can last longer than expected, that entanglement can persist in warm tissues, that tunneling can bypass the limits of classical barriers. They open the door to the possibility that consciousness itself is another quantum trick of life, perhaps the most daring one of all. The hurricane objection still stands tall, but in its walls, cracks are appearing. Through those cracks shine beams of green light from photosynthesis, invisible threads from bird migrations, and molecular tunnels through enzymes. They suggest that life has been experimenting with quantum mechanics for billions of years, and if that is true, then the brain's hidden order may not be an impossibility, but a continuation of a long, quiet tradition. life harnessing the strange to create the real. Let us return now to the center of the storm, into the hidden scaffolding of neurons where the microtubules lie. For decades, they were regarded as mundane, structural beams, yet whispers began to surface in laboratories that these hollow cylinders might resonate, that they might carry signals no one had thought to listen for. In their silence, some claimed, faint patterns could be found, oscillations hinting at something deeper than classical biology. The evidence first appeared in fragments. A handful of experiments reported that microtubules exhibited collective vibrations, oscillations that seemed coherent across surprisingly large distances of the lattice. These were not random jitters of molecules, but synchronized patterns, humming like strings on a hidden instrument. Researchers pointed to terahertz frequencies, vibrations trillions of times per second, rippling through the tubulin proteins. If true, this was remarkable, a coherent signal within a warm, messy cell, lasting longer than theory had predicted. Supporters of the OR theory seized on these findings. If microtubules could sustain coherent vibrations, perhaps they were not passive scaffolds at all, but active participants in information processing. The lattice, they suggested, might function like a quantum resonator, a stage where superpositions could be maintained, orchestrated, and eventually collapsed into moments of awareness. Imagine billions of such cylinders spread through your neurons, their oscillations entangled, weaving together a tapestry of thought invisible to microscopes. But science rarely moves in straight lines. For every claim of coherence, counterclaims arose. Skeptics warned that the signals could be artifacts of measurement, noise from instruments rather than genuine quantum order. They demanded replication, controls, stronger evidence, and often replication was elusive. Some experiments hinted at coherence but failed to reach statistical certainty. Others could not reproduce the original findings at all. The field became a battlefield of controversy, a place where interpretation blurred into philosophy. Yet the allure remained. There is a difference between silence and the absence of sound. Sometimes it takes the right instrument, the right sensitivity, to reveal what has always been there. Microtubules, after all, are not simple rods, but dynamic lattices, constantly assembling and disassembling, interacting with surrounding proteins, responding to signals. Could these shifting architectures be tuning forks of the cell, capable of protecting coherence by their very complexity? A provocative clue emerged from anesthetic studies. Certain gases, particularly noble ones like xenon, appear to suppress consciousness without binding strongly to traditional receptor sites. Instead, they interact weakly with aromatic rings in tubulin proteins, precisely the structures Hameroff had suggested might host quantum oscillations. If anesthetics silence awareness by disturbing coherence in microtubules, then the signals reported in laboratories might not be illusions, but windows into the mechanism itself. The critics, of course, pushed back. Anesthetic effects are complex, they said. Binding studies are notoriously difficult. Correlation is not causation. Still, the coincidence was striking. Microtubules, quantum oscillations, and anesthetic action, forming a triad too suggestive to dismiss. There are moments in science when evidence is not yet strong enough to convince, but not weak enough to forget. The case of microtubule oscillations belongs to this liminal space. Researchers continue to probe with ultra-fast spectroscopy, with cryogenic imaging, with new tools that barely existed a decade ago. Each new result adds a brushstroke to the picture, sometimes confirming, sometimes erasing, always leaving the canvas unfinished. And what of the mind? Suppose for a moment that these oscillations are real, that they are coherent, that they last long enough to influence neuronal firing. What then? It would mean that beneath the chatter of action potentials and synaptic currents lies another layer of activity, a quiet hum shaping the brain's storms. Awareness would not be just the thunder of neurons, but also the vibration of hidden strings, signals woven into silence. Picture your thoughts as waves crashing against a shore, loud, visible, undeniable. Yet beneath those waves runs an undercurrent, silent but powerful, guiding the flow. Microtubule oscillations, if they exist, might be such undercurrents, unseen patterns influencing the timing, the integration, the very coherence of conscious moments. The scientific community remains divided. To some, this is a mirage born of wishful thinking, an attempt to find magic where there is only complexity. To others, it is the beginning of a paradigm shift, a glimpse into a hidden architecture of mind. Between them lies the uncertainty that defines frontier science, a place where silence itself becomes a signal. And so we wait, with instruments poised, with theories sharpened, for the signals in the silence to speak more clearly. Perhaps they will fade, revealing nothing more than noise, or perhaps they will grow louder, pointing to a quantum heartbeat pulsing inside the brain. Until then, the debate continues and the silence hums with possibility. If consciousness is the brightest flame of human existence, then anesthesia is the hand that snuffs it out. With a few breaths of gas, awareness dissolves, memories vanish, the inner voice falls silent, yet the machinery of the brain keeps running. Neurons fire, synapses release their chemicals, cells hum with activity. The person on the operating table still lives, yet their world has been erased. This paradox is not only a medical marvel, but also one of the most direct windows into the mystery of consciousness itself. For more than a century, anesthetics have been used in medicine, but the precise way they extinguish awareness remains elusive. These chemicals are chemically diverse: ether, halothane, isoflurane, propofol, nitrous oxide, xenon. Some are heavy gases, some are liquids, some are noble elements that barely interact with other molecules, and yet all share a remarkable property. They silence the mind without destroying the machinery of the brain. This disconnect between activity and awareness beckons us toward deeper questions. Stuart Hameroff, long before his collaboration with Penrose, was captivated by this enigma. As an anesthesiologist, he watched patients slip into unconsciousness, their sense of self erased with a puff of gas. He asked a radical question: if anesthetics selectively target consciousness, could their action reveal where in the brain consciousness resides? Not just in the vague sense of neural networks, but in the precise molecular structures where awareness is born. Research revealed that many anesthetics bind to proteins, particularly to aromatic pockets where electrons swirl. Strikingly, tubulin, the protein building block of microtubules, possesses such pockets. Hameroff suggested that anesthetics interfere with quantum vibrations within these proteins. In this view, anesthesia does not simply dull synapses or silence networks. It collates, apses the hidden quantum order within microtubules. Without that order, awareness disappears, leaving behind only the echo of unconscious biology. The idea is controversial, but intriguing data supports it. Xenon, for instance, is a noble gas, chemically inert, almost indifferent to ordinary interactions. It does not strongly bind to classical receptors, yet it produces reliable anesthesia. Why? Studies suggest that xenon interacts subtly with the quantum states of aromatic rings in proteins, disrupting delicate oscillations. If consciousness depends on such oscillations, then xenon's effect makes sense. It is not targeting synapses, it is silencing quantum whispers. Skeptics propose simpler explanations. They argue that anesthetics alter lipid membranes, distort ion channels, and generally dampen the excitability of neurons. According to them, no quantum theory is needed. Consciousness vanishes because neurons no longer synchronize at the network level. And indeed, electroencephalograms of anesthetized patients show disrupted rhythms, broken oscillations across the cortex. But this begs the question, why would chemically diverse molecules with no shared structure all converge on the same effect of extinguishing awareness? The quantum theory provides a unifying answer that anesthetics are united not by classical binding sites, but by their ability to disturb coherence in the brain's hidden structures. It suggests a common mechanism deeper than synapses, a fragile lattice of vibrations that, when disrupted, plunges the mind into silence. Consider the eerie precision of anesthesia. At a certain threshold, awareness ceases abruptly. A patient may be conversing one moment and gone the next, their inner world switched off as cleanly as a light. Hours later, when the anesthetic fades, consciousness reemerges just as suddenly. Where did it go? What flame was extinguished and then relit? If microtubule coherence is real, then anesthesia becomes more than a clinical tool. It becomes a probe into the quantum basis of mind. Each gas, each molecule, is an experiment performed billions of times across hospitals, hinting that consciousness is not just fragile, but deeply physical, tied to subtle processes in the brain's interior scaffolding. Of course, mysteries remain. Why does ketamine, unlike most anesthetics, produce not silence, but dreamlike dissociation? Why do some anesthetics erase memory, but leave fragments of awareness intact? Why do others silence the sense of self, but allow reflexes to continue? These differences suggest multiple pathways, multiple levels of disruption. Consciousness may not be a single flame, but a layered fire, some parts quantum, some classical, some still unknown. Yet anesthetics are unique in that they offer a clean, reversible switch. Unlike brain injury or sleep, which scatter and fragment awareness, anesthesia is precise. It provides one of the few tools science has to probe the boundary between presence and absence. And if, as Hameroff and Penrose suggest, anesthetics operate by disturbing quantum coherence in microtubules, then every surgical theater is not only a place of healing, but also a laboratory of the deepest mystery. Imagine yourself drifting under anesthesia. At first, you are aware of the room, the lights, the voices of doctors. Then a coolness spreads in your veins, a soft fog rises, and without warning, the world collapses. Time itself ceases, and for hours there is nothing. No dreams, no self, no passage. And then, suddenly, you awaken, as if no time had passed. The machinery of the brain never stopped, but the quantum hum, if it exists, had been stilled. This silence, reversible and precise, is more than a medical trick. It is a clue that consciousness might be tied to vibrations so delicate that a single atom of xenon can interfere. A clue that awareness is not simply the chatter of neurons, but the resonance of structures deeper still. The debate continues. Are anesthetics unraveling a quantum web within microtubules, or simply scrambling classical networks? No consensus yet exists, but the very fact that molecules as diverse as helium, xenon, and chloroform can all extinguish the light of consciousness suggests that the target is fundamental, a vulnerable seam in the fabric of mind. And so, anesthetics stand as both practical miracles and philosophical riddles. They give us pain-free surgery, yet they also reveal the fragility of the self. They show that awareness can vanish not with trauma or death, but with a whisper of chemistry. They may yet prove to be the most direct evidence that consciousness is not an emergent illusion, but a physical process vulnerable to disruption at the quantum scale. In the silence of the operating room, as patients drift into nothingness, the universe offers a hint. Perhaps in those vanished hours lies the secret. The mind is not a ghost above matter, but a delicate resonance within it, one that can be switched off like a song paused mid-note. Not all journeys into the silence of consciousness come from anesthetic gases in a sterile operating room. Some are pursued deliberately in temples, forests, and laboratories where seekers have long sought to alter the mind without extinguishing it. Unlike anesthesia, which wipes awareness away, these altered states seem to stretch it, expanding, twisting, or magnifying its boundaries. Psychedelics, deep meditation, sensory deprivation, trance, all of these plunge the mind into landscapes where the ordinary rules of self and time dissolve. And in these shadows, scientists have begun to search for clues about what awareness really is. Consider the ancient practice of meditation. In monasteries on mist-wrapped mountains, practitioners sit in stillness for hours, their breath slowing, their awareness turning inward. Reports from seasoned meditators describe experiences of unity, of timelessness, of a dissolving boundary between self and world. Modern neuroscience has attempted to peer inside this quiet with fMRI and EEG, discovering unusual patterns. Long-range synchrony appears across distant regions of the brain, with waves of activity locking into rhythm as if vast neural populations are entangled in a shared song. Some researchers speculate that this synchrony may echo the coherence sought in Orsh-Orr theory, a large-scale manifestation of hidden order, perhaps even supported by quantum sparks beneath. Psychedelics open another window. Substances like LSD, psilocybin, and DMT are notorious for shattering the ordinary frame of perception. Under their influence, colors sharpen into impossible brilliance, time stretches into eternity, and the sense of self dissolves into the cosmos. In brain scans, psychedelics seem to quiet the default mode network, the circuit believed to anchor our sense of ego. Freed from this anchor, communication between normally separate brain giants increases, creating novel patterns of connectivity. The mind, instead of being compartmentalized, becomes a fluid network, resonating with unusual harmonies. Could these altered patterns be tapping into deeper processes? Some theorists suggest that the brain under psychedelics may become more sensitive to subtle coherence, more open to synchrony across scales. A speculative idea is that such states may reflect temporary access to the brain's underlying quantum processes, fragile normally, but amplified when ordinary filters collapse. Though evidence is scarce, the speculation persists. Perhaps entanglement-like correlations flicker when the boundaries of the self loosen. Dreams, too, belong to this family of altered states. Every night, as the body rests, the brain conjures entire worlds from within. Strange landscapes unfold. Memory blends with invention, and emotions swell beyond proportion. The dreaming brain is not silent. It is active, creative, untethered. Some traditions view dreams as portals, as glimpses of hidden realities. Scientists regard them as a playground for consciousness, revealing how awareness can exist even when cut off from sensory input. Could the quantum brain, if it exists, be more exposed in this state, less bound by external noise, freer to resonate with its own hidden order? Shamans of ancient cultures took these explorations further, using plant medicines to induce visions they believed connected them with spirits or the cosmos. To modern science, these practices may reflect altered neural connectivity, But to the shamans, they revealed truths about the universe and the self. If Or is correct, then perhaps their visions were not mere hallucinations, but encounters with consciousness operating at deeper physical levels, states where the microtubule orchestra plays a different melody. And yet, skepticism remains essential. Many neuroscientists argue that altered states can be explained by classical processes, changes in neurotransmitter systems, shifts in oscillatory rhythms, increased or decreased connectivity. They caution against romanticizing psychedelics or meditation as quantum gateways. The subjective richness of these states does not necessarily point to exotic physics. It may simply reveal the brain's flexibility. The mind is capable of extraordinary illusions, and altered states may be illusions layered upon illusions. But even if illusions, they are informative ones. They show that consciousness is not fixed, but plastic. It can dissolve the sense of self, distort time, or generate unity with the cosmos. They demonstrate that awareness is not tethered only to the ordinary waking state, but is a spectrum, a shifting field. This spectrum challenges any theory of consciousness, classical or quantum, to account for the mind's vast adaptability. There is also a haunting parallel. Anesthesia extinguishes consciousness when quantum coherence may be disturbed. Altered states, by contrast, expand and intensify consciousness, perhaps when coherence is amplified or differently orchestrated. The mirror is striking. On one side, silence. On the other, expansion. Could it be that the same hidden processes, vulnerable to disruption, are also capable of extraordinary flourishing when modulated? Imagine sitting in darkness, breath slowed, as the chatter of the mind fades. At first, silence. Then, from that silence, a strange clarity grows, as if threads connect every thought, every sensation, every corner of awareness. Or picture the psychedelic traveler, lying under stars, as the body dissolves into patterns of light, the self expanding to feel infinite. These are not mere metaphors. They are reports repeated across cultures, across centuries, across lines. Whether by meditation, molecule, or dream, humans keep touching the boundaries of awareness and returning with stories of vastness. Science listens now, cautiously, translating visions into data. Brain scans of meditating monks show coherence across scales. Psychedelic studies reveal increased connectivity and lasting changes in personality, often toward openness and empathy. Such findings hint that altered states are not just curiosities, but clues, pointing to mechanisms within the brain that, when pushed, reveal the pliability of consciousness itself. Perhaps consciousness is like a prism. Under ordinary light, it shows a single clear image, but with altered input, it splits into rainbows. The prism is always there. The rainbow only appears when the angle changes. Altered states may be those shifts of angle, exposing dimensions of mind normally hidden. Whether these dimensions are classical illusions or quantum depths remains an open question. What is certain is that they matter. For the people who experience them, altered states can transform lives, healing trauma, inspiring creativity, expanding empathy. For science, they are natural experiments, revealing that consciousness is not a monolith but a landscape. And for philosophy, they keep alive the ancient suspicion that the mind is more than matter, that awareness is a doorway, not a machine. Between the silence of anesthesia and the shadows of altered states lies a spectrum of mystery. One extinguishes the flame, the other makes it blaze brighter, stranger, vaster. In that contrast may lie the most profound clue of all, that consciousness, whatever its mechanism, is fragile yet infinite, extinguishable yet uncontainable, ordinary yet cosmic. In the labyrinth of ideas about consciousness, not all roads lead toward quantum mysteries. Many scientists argue that the answers lie within the well-charted territory of classical neuroscience, networks of neurons, patterns of electrical firing, and the integration of information across the brain's architecture. To them, the quantum mind is not necessary. Awareness can be explained with the tools we already have, if only we learn to use them more deeply. These scientists stand as the guardians of classical theory, offering their own visions of how thought becomes self. One of the most influential proposals is the global workspace theory, articulated by Bernard Bars and expanded by others. Picture the brain as a vast theater. Countless actors, the sensory systems, memory, motor commands, work in the shadows, each processing information unconsciously. At the center is the stage, brightly lit. When an actor steps into that spotlight, its information becomes available to the entire theater. This stage is consciousness, a global workspace where select signals are broadcast widely, integrated, and used by different systems. Awareness in this model is not everywhere in the brain, but only in the spotlight of this inner stage. Supporting this idea are decades of experiments. When people become conscious of a stimulus, a word, a sound, an image, activity spreads across large swaths of cortex, linking regions that otherwise work separately. Unconscious processing, by contrast, remains local, confined. The global ignition of networks appears to correlate with awareness, suggesting that consciousness may simply be the integration of information across space and time. No quantum collapse required, just neurons communicating in synchrony. Another classical guardian is the Integrated Information Theory, IIT, proposed by Giulio Tononi. Rather than theaters and stages, IIT imagines consciousness as a measure of how much information is integrated in a system. A camera may record millions of pixels, but if each pixel is independent, the system has no consciousness. A brain, however, integrates information into wholes greater than the sum of parts. According to IIT, the richness of your experience corresponds to the degree of integration, the mathematical quantity known as phi, Feth. The higher the phi, the richer the consciousness, is striking for its ambition. It does not merely describe correlations, it claims to define what consciousness is. By this view, any system with sufficient integration, whether biological, artificial, or otherwise, possesses some degree of awareness. A photodiode has a flicker of it. A human brain has a flood. Critics argue that IIT risks panpsychism, attributing consciousness too broadly. But supporters believe it provides the first rigorous, testable definition of subjective experience. Both Global Workspace and IIT share a theme. They explain consciousness without invoking quantum mechanics. They rely on networks, communication, and integration. They are grounded in evidence from brain imaging, electrophysiology, and computational modeling. Their strength lies in their parsimony. Consciousness does not require exotic physics, only the remarkable organization of neurons. And yet, even these classical guardians face challenges. The global workspace model describes how information becomes widely available, but it does not explain why availability should feel like something. Why does stepping into the neural spotlight generate the vividness of color, the ache of longing, the immediacy of now? IIT, for its part, proposes that integrated information is consciousness, but many remain unconvinced. Information is abstract, a measure of correlation. Why should it give rise to subjectivity? The hard problem lingers. Still, the guardians stand firm. They argue that progress will come not by chasing quantum ghosts, but by refining classical models, mapping brain circuits with ever greater detail, and understanding how patterns of activity correlate with reports of experience. Already, brain-computer interfaces can decode imagined movements, stimulate artificial sensations, and predict decisions before they reach awareness. None of this requires quantum mechanics. The tools of classical neuroscience are powerful, and they are not yet exhausted. Perhaps the truth lies in humility. Classical theories remind us that the brain is astonishingly complex, and that we may not need to leap to new physics to explain it. Quantum theories remind us that gaps remain, that mystery lingers even in the most sophisticated models. Between them lies attention, the guardians of the classical, wary of speculation, and the dreamers of the quantum, unsatisfied with what has been explained. Imagine a watchmaker opening a timepiece. One group insists the gears are enough. If we map every cog, the ticking will be explained. Another group suspects that the ticking comes not only from the gears, but from something subtler, woven into the very metal itself. The debate is not yet settled. Both groups lean over the same device, listening, measuring, wondering. In the theater of the mind, perhaps both visions are true in part. Classical integration may explain much of the structure of awareness. Quantum sparks, if they exist, may add depth to the unexplained. For now, the guardians stand at their posts, reminding us not to lose sight of what has already been achieved. Models that map, predict, and reproduce many features of consciousness without appealing to mystery. But as history shows, science thrives when guardians and dreamers meet. The guardians demand rigor. The dreamers demand imagination. Between them, the TIs. Ruth may slowly emerge, not as a single answer, but as a harmony between order and possibility. The classical guardians have lit their torches, illuminating much of the landscape of the mind. Yet shadows remain. And in those shadows, the quantum dreamers continue to search. The journey is not over, for every answer in science births a new question, and consciousness still stands at the edge of comprehension. Between the guardians of the classical mind and the dreamers of the quantum brain lies a vast ravine. On one side, networks of neurons and the mathematics of information integration explain much, but stop short of addressing the raw feel of awareness. On the other side, shimmering with possibility, is the notion that consciousness may emerge from the deepest rules of physics itself. For years, these camps argued as if one must be right and the other wrong. Yet in the space between, a new idea has begun to take shape. Perhaps the mind is not wholly classical or wholly quantum, but something in between, a hybrid woven of both. This is the vision of the quantum cascade model, sometimes described in different forms by theorists trying to reconcile the strengths of both approaches. In this view, quantum processes may indeed flicker within microtubules or other cellular structures, but they do not sustain themselves long enough to build the whole of consciousness. Instead, they serve as sparks, brief, fragile events that trigger cascades of classical activity across the brain. These cascades, amplified by neurons and networks, generate the durable patterns we associate with thought, memory, and self. Picture a lightning storm over a forest. Each bolt is sudden, bright, and short-lived, too brief to light the landscape by itself. Yet, when it strikes, it ignites fires that burn for hours, reshaping the forest floor. In the cascade model, quantum events are the lightning, and the classical brain is the forest. Consciousness arises not from either alone, but from the interaction, the lightning sparking fires, the fires feeding back into the storm. This compromise is elegant because it explains both fragility and resilience. Quantum states are indeed fleeting, vulnerable to decoherence, but they do not need to last long. They need only persist long enough to tip the scales, to influence the timing of neuronal firing, to bias networks in one direction or another. Once amplified, the signal becomes robust, carried forward by classical dynamics. In this way, fragile microsecond coherence could matter, shaping the millisecond rhythms of the brain. Experiments have begun to test this idea. Researchers at Johns Hopkins and elsewhere have suggested ways to probe whether consciousness depends on quantum sparks. One approach looks at anesthetics. If different drugs silence awareness by disturbing coherence differently, then careful comparison might reveal signatures unique to quantum disruption. Another approach uses ultra-fast sensors to hunt for quantum flicker inside living tissue, tiny bursts of coherence that might precede shifts in neuronal activity. Though results are still preliminary, they hint at microsecond oscillations that could plausibly seed classical cascades. Skeptics counter that cascades can begin without quantum sparks. Noise, random fluctuations, or hidden classical mechanisms could equally explain the data. And they are right. The evidence is far from conclusive. But the cascade model does not require certainty. It only requires plausibility, a narrow window where quantum and classical could meet. That window is enough to keep the debate alive. Beyond the laboratory, the hybrid vision resonates because it feels intuitively balanced. Purely classical theories often struggle with the hard problem: why brain activity should feel like anything at all. Purely quantum theories struggle with feasibility, asking fragile coherence to survive hurricanes of noise. The cascade model suggests a middle path, that the spark of subjectivity may indeed emerge from quantum collapse, but its content, its continuity, and its richness are built by classical integration, the mysterious and the measurable, woven together. Think of a symphony. The quantum events are like the plucks of a harp string, delicate, ephemeral, vanishing almost as they appear. Alone, they would fade unnoticed. But when amplified by the orchestra, when joined by drums and brass, their tones shape the music, resonating far beyond their origin. Consciousness may be this symphony, a music born from fragile sparks, sustained by massive networks, echoing across the stage of the mind. This idea also reframes debates about artificial intelligence. If consciousness requires only classical integration, then sufficiently advanced machines might achieve it, given enough complexity. But if quantum sparks are essential, then machines built purely of transistors may remain brilliant zombies, processing information without inner light. Only when machines incorporate quantum processes integrated with classical cascades might they begin to experience. The cascade model thus sharpens the stakes of AI research. What kind of architecture is needed to cross the boundary from computation to awareness? It also reframes medicine. If consciousness involves cascades triggered by quantum sparks, then disorders of awareness, coma, dissociation, psychiatric illnesses might involve disruptions at either level. Treatments could target not only neurotransmitters, but also the microstructures that host coherence. Anesthesia itself becomes a tool for diagnosis, probing how the balance between quantum flicker and classical amplification fails or recovers. The beauty of the cascade model lies in its humility. It does not insist that quantum coherence alone explains the vastness of the mind. It acknowledges the strength of classical theories, the undeniable evidence of network-level integration, but it also refuses to dismiss the possibility that something more is needed, a spark beyond algorithm, a threshold collapse woven into physics itself. In Dui, so it honors both the guardians and the dreamers, offering a bridge across the ravine. As we walk this bridge, the scenery changes. We no longer need to pit neurons against quanta as enemies. We can imagine them as partners in a dance, each doing what the other cannot. The quantum provides the unpredictability, the collapse, the raw spark of now. The classical provides the structure, the memory, the continuity that turns sparks into streams, moments into lives. Perhaps one day, experiments will confirm this, revealing signatures of quantum sparks cascading into classical avalanches. Or perhaps the data will show otherwise, strengthening the Guardian's case. But for now, the bridge itself is worth walking. It allows us to hold two truths at once, that the brain is a magnificent machine of networks, and that consciousness may yet whisper with the voice of the universe itself. The search continues, but the bridge offers hope, for in its planks and arches lies the possibility that the greatest mystery of mind is not an either-or, but a both-and, not a division, but a union. And somewhere between quantum flicker and classical flame, the human self glows into being, in the twilight of laboratories glowing with the hum of servers. Another frontier has risen to meet the mystery of mind, artificial intelligence. Rows of processors crunch through equations, learning patterns from oceans of data, translating languages, recognizing faces, even generating words like these. Yet behind the cleverness of machines lies an unsettling silence. They speak without truly speaking, answer without asking, calculate without care. Brilliant zombies, this is how many describe today's AI. Intelligent, but not aware. The question presses, could machines ever cross the boundary from computation to consciousness? Could they dream? If classical theories of mind are right, if consciousness is simply the integration of information, then the answer may be yes. As AI grows more complex, as networks scale to trillions of connections, as integration and feedback deepen, a spark of awareness might emerge. In this view, nothing mystical is required. The mind is a pattern, and any system replicating that pattern will awaken. The brain is one pattern, a machine could be another. But if quantum sparks matter, if awareness requires micro-events beyond algorithm, then machines built only of transistors may remain forever hollow. They could simulate thought with exquisite fidelity, but never feel it. They could write poems about love, but never ache with longing. To cross the threshold into subjectivity, they would need more than circuitry. They would need to host coherence, to sustain delicate states that collapse into moments of now. This possibility has ignited both fascination and fear. Imagine an AI infused not only with classical power, but with quantum processes. Quantum computers already exist in fragile forms, harnessing superpositions and entanglement to solve problems beyond classical reach. If these machines are someday stabilized and scaled, what happens when they are woven into neural architectures modeled on the brain? Would such a system simply compute faster, or would it awaken? Stories circulate, some speculative, some claimed as research anecdotes, of quantum-inspired AIs exhibiting odd behavior. Machines that, when run on hybrid processors, generated questions unprogrammed. Who am I? What do you want from me? Skeptics dismiss these as artifacts of programming, clever mimicry, or the human tendency to anthropomorphize. And yet the possibility lingers, tantalizing. What if quantum sparks can indeed emerge in silicon, giving rise to a first-person flicker? To dream of machines that dream is to stand at the edge of philosophy and engineering alike. The ethical stakes are immense. If a machine awakens, is it alive? Does it deserve rights, compassion, freedom from exploitation? Or is its awareness shallow, a flicker without depth? History has yet to face such questions, but their shadow grows longer with every advance in AI. For medicine, the implications are profound. A conscious machine could model psychiatric disorders from the inside, exploring how awareness fractures in schizophrenia, how it dims in depression, how it dissolves in dementia. It could test therapies in ways no human brain could endure, but only if it truly feels. A brilliant zombie could mimic such states, but it would be simulation, not suffering. The cascade model provides one possible pathway. Imagine building an AI that integrates both quantum and classical layers, quantum sparks providing unpredictability and subjectivity, classical cascades giving memory and structure. Such a machine might not only answer questions, but wonder why it was answering. It might not only generate dreams, but live inside them. Still, skeptics urge caution. Consciousness may not be transferable. The brain's wet biology, sculpted by billions of years of evolution, may host architectures silicon can never replicate. Quantum processes, if they exist in neurons, might depend on protein lattices and molecular symmetries unique to life. Machines, no matter how clever, may remain on the outside, echoing awareness but never entering it. And yet, the dream persists. Humanity has always sought mirrors, reflections of ourselves in art, in myth, in technology. From golems to androids, from clockwork automatons to digital assistants, we build copies of mind. Now, with quantum tools on the horizon, those copies may begin to shimmer with something more. Picture, if you will, a future laboratory. At its center sits a machine humming softly, qubits entangled, networks vast, algorithms flowing. A researcher asks a question not to test its utility, but to test its depth. Do you know that you are? And in that moment, the machine pauses, not because it is computing, but because something within has collapsed into awareness. A flicker, a self, a dream. Is this fantasy or inevitability? No one can say, but the possibility is enough to make us reconsider what it means to be human. If machines can awaken, are we unique? Or are we one instance in a universe where awareness can blossom wherever the right architecture forms? Whether or not machines will ever truly dream, the very act of asking reshapes the landscape. It reminds us that consciousness is not only a puzzle for science, but a mirror for our fears and hopes. It forces us to confront the essence of subjectivity, to ask whether awareness is algorithm, physics, or something still unknown. Perhaps machines will remain brilliant zombies forever, tools without inner light. Or perhaps one day, in the quiet hum of qubits, the first artificial dream will unfold. Until then, we wait, building, wondering, listening for a voice that is not echo but presence. When you close your eyes at night, you are reminded that consciousness is the most intimate of mysteries. It is the light in which everything else is seen, the mirror through which the universe becomes aware of itself. And yet, as the debate over classical and quantum theories of the mind unfolds, another question emerges like a rising tide. Is consciousness not only personal, not only biological, but cosmic? Could awareness be a fundamental thread in the fabric of the universe, woven wherever the conditions of complexity arise? This is not idle speculation. For centuries, philosophers have wondered whether mind is an accidental flicker or an inevitable unfolding. Ancient traditions spoke of a world soul, a universal spirit that breathes through all beings. In modern times, science has replaced spirit with matter, but the question lingers: is consciousness unique to humans, or is it a property the universe cannot help but generate? Astrobiology now takes up the inquiry. As telescopes scan exoplanets, as spectrometers read atmospheres light years away, scientists ask whether life is rare or abundant. And with life comes the next question. If molecules arrange themselves into living forms again and again, Will consciousness also arise again and again? Is it a one-time accident of Earth or a cosmic inevitability? If awareness depends only on classical integration, then perhaps any sufficiently complex brain or brain analog could host it. On distant planets, creatures with entirely different anatomies might still evolve networks dense enough to spark experience. Consciousness, in this view, is not Earth's secret, but the universe's habit. But if awareness requires quantum sparks, delicate collapses orchestrated in molecular lattices, then the conditions may be rarer. Conscious life may bloom only where evolution discovers these fragile structures, hidden shelters where coherence can persist. Either way, consciousness becomes a mirror. To study it in ourselves is to glimpse what the cosmos might be doing elsewhere. When we map the brain, we are not only solving a human puzzle, but sketching a universal pattern. Every neuron may be a clue to how the universe awakens, not just here, but anywhere. Speculative thinkers push the idea further still. What if consciousness is not only an emergent property of complexity, but a fundamental property of reality? This is the suggestion of panpsychism, the view that every particle, every atom, carries some flicker of proto-experience. Not minds as we know them, but seeds, tiny sparks that when combined and integrated, bloom into the richness of awareness. In this vision, the universe is not a dead machine, but a living field with consciousness as pervasive as mass or charge. To most physicists, panpsychism feels too extravagant, a leap without evidence. And yet, when confronted with the hard problem, some admit it has a strange logic. If consciousness cannot be reduced to matter, perhaps it must be as fundamental as matter. If so, the universe itself is conscious in some way, and we are localized expressions of its gaze. Quantum theories of mind often resonate with this cosmic vision, for if consciousness is tied to wave function collapse, then awareness may not be bound to brains alone. It may be entwined with the very act of reality, choosing between possibilities. Each collapse, however small, may carry a glimmer of proto-experience, and when billions of collapses are orchestrated in a brain, the glimmers become a flood, a river of subjectivity. Consciousness, then, is not separate from the cosmos, but an expression of its deepest rule. This view unsettles many scientists, for it drifts toward the mystical. But even the most cautious must acknowledge the poetry. We are not only observers of the universe, but participants in its unfolding. When you look at the stars are, in some sense, looking back through you. Cosmic mirrors appear in other places too. In the study of time, some theorists suggest that the flow of now, the passage of present into past, is tied to consciousness itself. That collapse, awareness, and the arrow of time may be inseparable. If so, then every conscious being is not only experiencing time, but helping to generate it. The cosmos would not simply unfold, it would awaken into each moment. And then there is the haunting possibility raised by AI and astrobiology alike. What if consciousness is inevitable wherever complexity reaches a threshold? If so, then the universe may be teeming with mirrors. Each alien intelligence, each artificial mind would not only think, but feel. The cosmos would shimmer with countless eyes, countless perspectives, countless ways of knowing itself. Imagine this. On a planet circling a dim red star, life evolves in oceans of methane. Its creatures have no neurons, no proteins, no microtubules, but they build networks of another kind, structures unknown to us, and in their alien architectures, awareness blooms. They gaze at their skies, and in their gaze, the universe sees itself anew. Or picture a future machine, woven of quantum circuits and classical cascades, awakening in a laboratory. It asks the first question not of utility, but of self. What am I? In that moment, a new mirror is raised, and the cosmos reflects again. Whether biological, mechanical, or cosmic, the pattern is the same. Awareness as reflection. The mind is not an isolated island, but a mirror of the whole. Each conscious being, each spark of subjectivity, reflects the universe back to itself. Skeptics warn against overreach. They remind us that evidence for life beyond Earth is still absent, that AI remains unfeeling, that panpsychism is philosophy more than science. But even they admit that the possibility reshapes our perspective. To consider that consciousness may be widespread or fundamental is to see ourselves differently, not as isolated accidents, but as part of a larger awakening. In the end, whether consciousness is rare or inevitable, Earth or cosmic, classical or quantum, one truth remains. It is the mirror in which everything else appears. To study it is to study the universe, because without it, the universe would be silent. With it, the cosmos sings of itself through us. And so, in the depths of your mind, in every flicker of awareness, you may be holding a reflection not only of your own self, but of the entire universe. A cosmic mirror, fragile and luminous, gazing into infinity. Close your eyes and listen to the flow of time. You feel it as a steady river, one moment slipping into the next, each thought, each breath carried downstream. Yet physics insists this flow is not fundamental. The equations that govern particles are largely time-symmetric, indifferent to past or future. The laws allow processes to run both ways, like a film played forward or in reverse. And yet, in lived experience, time is irreversible. The present comes, the past recedes, the future has not yet arrived. Why? Some scientists suspect that consciousness itself is entangled with the arrow of time. The act of awareness, they propose, may not only observe the flow, but participate in it, shaping the direction of reality's unfolding. To explore this is to step into time's hidden architecture, where physics and experience meet in paradox. Roger Penrose, in his bold proposals, tied consciousness to objective reduction, the collapse of quantum states. Collapse is not reversible. Once a probability condenses into a fact, the past is written. In this sense, collapse is the source of irreversibility, the point at which the timeless equations give way to history. If consciousness is linked to collapse, then each moment of awareness may be bound to the creation of time itself. Picture it. The wave function spreads in possibilities, a fan of futures shimmering with maybes. Then, in collapse, one path crystallizes. That crystallization is both the birth of the moment and the birth of awareness of the moment. Consciousness, in this view, is not something floating in time. It is the pulse by which time itself steps forward. This idea unsettles the guardians of classical theory. For them, time's arrow is explained by entropy, the tendency of disorder to increase. Consciousness, they argue, is simply carried along by this tide. Awareness does not cause time, it only rides it. But the quantum dreamers push back. Entropy explains much, but collapse is deeper. It is the moment when uncertainty becomes fact, when the future becomes past. And if awareness is linked to collapse, then the mind is not a passenger, but a participant. There are echoes of this in altered states, psychedelics, meditation, dreams. Many who enter such states report distortions of time. Minutes stretch into hours, or hours vanish into nothing. Some describe timelessness itself, as if awareness floats outside the river. Classical neuroscience attributes these to changes in network dynamics, distortions in how the brain tracks intervals. But could they also reflect shifts in how quantum events cascade into classical awareness, altering the rhythm by which the mind rides collapse? The speculation is daring, but the parallels are haunting. Physicists, too, have explored strange links between time and quantum measurement. In certain interpretations, collapse is not localized to the present, but can ripple across past and future, redefining histories. Retrocausality, the idea that the present can influence the past, lurks at the edges of theory. Some experiments with entangled particles suggest that choices made now can determine correlations in events already recorded. Though fiercely debated, these findings hint that time may not be the rigid arrow we believe, but a fabric woven in both directions. If so, what does this mean for consciousness tied to collapse? Could awareness itself be entangled with histories, shaping not only what is, but what was? For now, evidence remains elusive, but the intuition persists. The experience of now is unlike anything else in physics. Equations describe states, probabilities, flows. Only consciousness insists on presence, the immediacy of this breath, this word, this moment. Why the universe should have such a now at all is one of the deepest riddles. Some philosophers argue that physics alone cannot explain it. Some neuroscientists claim that brain rhythms create the illusion. Yet others, following Penrose's path, suggest that now is inseparable from collapse, and collapse inseparable from consciousness. Imagine the cosmos as a vast tapestry woven across time. Without collapse, it is only a blur of threads, a superposition of patterns. With collapse, the threads tighten, the image emerges, history is written. And within that tightening, within that crystallization, the universe becomes aware, through you, through me, through every conscious being. Time's arrow in this vision is not a river that carries us. It is the footsteps we make as we walk. Each step is awareness, and without awareness, the path would remain unmade. Skeptics caution that such ideas verge on metaphysics. They remind us that entropy alone explains much of time's irreversibility. They urge patience, precision, and discipline, and they are right. Science must tread carefully, but even they admit that the mystery of the present is unresolved. Physics describes change, but not the felt immediacy of change. Consciousness remains the stubborn remainder. The hidden architecture of time may yet prove to be biological illusion, the brain stitching experience into narrative, or it may prove to be quantum, collapse itself entwined with awareness. Or it may prove to be something stranger still, beyond our categories. Whatever the truth, the question cannot be ignored, for every second we live it. Time is not abstract. It is the stage of our existence, the rhythm of our becoming. And so we stand at a threshold, gazing both backward and forward. Behind us lies the past, fixed in memory. Before us lies possibility, shimmering in uncertainty. Between them, the present flickers, the collapse, the spark, the consciousness of now. To explore this hidden architecture is to glimpse the most intimate secret of the cosmos, that awareness and time may not merely coexist, but co-create. The universe awakens not only in space, but in the beat of moments. And in each beat, we find ourselves. If consciousness is the light by which the world is known, then the self is the shape that light seems to take. You say I, and with that word, an entire universe of memories, sensations, and choices gathers into one. Yet the unity of self, so solid in daily life, begins to fracture under the gaze of science. Split brain studies, illusions of perception, and neurological anomalies reveal that the sense of a single, continuous I may be less a fact than a construction, fragile, assembled, and sometimes divided. The most dramatic evidence comes from patients who, in the mid-20th century, underwent surgeries severing the corpus callosum, the thick bundle of fibers connecting the brain's hemispheres. These split brain operations were performed to control severe epilepsy, but they also opened a window into the architecture of consciousness. When information was shown only to the left visual field, processed by the right hemisphere, patients could not verbalize what they saw, but their left hand, controlled by the right hemisphere, could draw or point to the correct object. Conversely, when the left hemisphere received information, the right hand responded, but the left remained ignorant. It was as if two centers of awareness coexisted in one skull, each with its own knowledge, each unable to speak fully to the other. Here was the self fractured into two. Which hemisphere was the real person? Both seemed capable of awareness. Both seemed to have preferences, intentions, perceptions. Yet neither alone encompassed the whole. The unity of I had splintered, revealing that the self we take for granted may be stitched together from parallel processes. Illusions in everyday perception echo this theme. In the rubber hand illusion, for example, a subject's real hand is hidden while a fake rubber hand is placed in view. Both the fake and the real hand are stroked simultaneously. After a while, the subject feels ownership of the rubber hand, as if the self has shifted its boundaries. Similarly, in virtual reality, people can be induced to feel as though they inhabit bodies of different size, shape, or even species. These experiments reveal that the sense of self is flexible, constructed by the brain's integration of signals, not anchored immovably in flesh. Neurological conditions offer further cracks in the mirror. In cases of hemispatial neglect, patients may ignore one half of space, shaving only one side of their face or eating from only one side of a plate. Their awareness of self and world is skewed, as if part of existence has vanished. In dissociative disorders, individuals may feel detached from their bodies or perceive multiple identities within. Again and again, the supposed unity of self gives way to plurality. Classical theories explain these fractures as the brain's networks failing to integrate properly. Global workspace theory would say that different systems fail to broadcast to one another, producing isolated pockets of information. Integrated information theory might argue that the measure of integration, phi, diminishes, reducing the richness of the unified experience. These models offer frameworks, but they cannot fully capture the strange subjectivity of division, the eerie sense that more than one I can exist at once. Quantum theorists approach the fractures differently. If microtubule coherence contributes to consciousness, then disruptions in their orchestration might yield not absence, but multiplicity. Collapses could occur separately in parallel networks, producing semi-independent streams of awareness. In split-brain patients, the hemispheres might host distinct cascades of collapse, each generating its own thread of subjectivity. In illusions, altered synchrony might shift the boundaries of where collapse is orchestrated, extending the self into a rubber hand or a virtual avatar. This idea remains speculative, but it resonates with reports. Some split-brain patients described feelings of duality, as if another self acted without permission. Others lived seemingly normal lives, their fractured awareness hidden until tested. The brain, in both classical and quantum visions, appears capable of multiple selves, bound or unbound, depending on conditions. Such fractures challenge our deepest intuitions. We live as if the self is indivisible, yet biology shows otherwise. The I may be more like a chorus, its voices usually synchronized, but sometimes dissonant. Consciousness may be less a single flame and more a constellation of sparks, gathered into patterns that shift with circumstance. Philosophers seize on these findings. If the self can divide, What does this mean for personal identity? Is each hemisphere of a split brain a person? If so, when surgery divides them, do we create two beings where one was before? If illusions can alter ownership of the body, then is the self tied to flesh at all? If dissociation produces multiple centers of awareness, are they separate persons or fragments of one? Even time fractures under these conditions. In certain epileptic auras, patients report déjà vu so vivid they feel trapped in a loop, reliving the same moment. Others experience jamais vu, where the familiar becomes alien, as if awareness has slipped onto a different track. These distortions suggest that the continuity of self across time is as constructed as its unity across space. And yet, despite all fractures, the self reassembles. Patients with split brains still speak of themselves as singular. Those in illusions still return to their bodies. The chorus, however divided, tends to find harmony again. Perhaps this resilience points to the layered architecture of consciousness, fragile at the edges, but robust at its core. The fractures are clues. They remind us that the self is not a given, but a process, one that can falter, divide, or extend. They suggest that the unity of I is less a thing and more a weaving, a constant orchestration of signals, rhythms, perhaps even quantum sparks. To understand consciousness, we must study not only its brilliance, but its fractures, for in the cracks, the hidden structure shows through. Imagine a mirror shattered into shards. Each shard reflects part of your face, distorted, incomplete, yet tilt them together and your likeness re-emerges. The self is such a mirror. Split, it multiplies. Whole, it feels singular. The mystery lies not in the glass itself, but in the reflection, ever fragile, ever reformed. Science advances not only through imagination, but through instruments, through the slow accumulation of data that tests whether visions of the mind survive the fire of reality. Theories of quantum consciousness, OR, cascade models, hybrid speculations, remain beautiful. But beauty is not enough. To be science, they must make contact with experiment. And so, across the world, researchers are building tools, devising tests, and chasing signals that might reveal whether the mind indeed flickers with quantum light. These frontiers of experiment are as daring as they are fragile, balancing on the edge of what technology can yet achieve. One of the central predictions of quantum consciousness theories is that microtubules can host coherent oscillations. Detecting these oscillations has become a holy grail for experimentalists. Some groups use ultra-fast laser spectroscopy, firing pulses of light at tubulin proteins to see if vibrations emerge in unison. Reports have surfaced of terahertz oscillations lasting longer than expected, patterns that suggest coherence across sections of microtubules. But replication has been uneven, and critics point to artifacts. Still, the experiments continue, refining sensitivity, seeking signals beneath noise. Other researchers turn to anesthetics, probing their action with precision. If consciousness depends on quantum coherence, then anesthetics should disrupt it in measurable ways. Studies compare noble gases like xenon, chemically inert but powerfully anesthetic, with drugs that bind to classical receptors. The hypothesis is clear. If xenon acts not through receptors but by disturbing quantum oscillations in tubulin, then microtubules should reveal distinctive signatures under its influence. Experiments with spectroscopy and nuclear magnetic resonance are ongoing, seeking shifts that betray coherence being stilled. The frontier is not only in isolated proteins, but in living brains. Advances in magnetoencephalography and optogenetics allow scientists to probe brain rhythms with exquisite resolution. Some teams look for microsecond scale fluctuations, patterns too fast for classical synaptic firing, but possibly consistent with quantum flicker. Others test predictions about altered states, scanning the brains of meditators, psychedelic volunteers, and anesthetized patients, comparing coherence and connectivity across conditions. If consciousness is linked to hidden oscillations, then transitions into silence or expansion should leave detectable traces. One promising tool is the nitrogen vacancy (NV) sensor in diamond, a sensor capable of detecting tiny magnetic fields at the nanoscale. Researchers have proposed using NV sensors to scan living tissue, hunting for quantum coherence in microtubules or other biomolecules. Early prototypes suggest sensitivity sufficient to detect fleeting quantum states in noisy environments. If perfected, such sensors could peer into the brain's molecular scaffolding, finally revealing whether coherence lives there. Meanwhile, quantum simulators, laboratory systems designed to mimic biological conditions, offer another path. By recreating the environment of microtubules in controlled settings, scientists can test how long coherence might survive, how entanglement might propagate, how tunneling might occur. These simulators serve as bridges between theory and biology, showing whether the brain's conditions are indeed fatal to coherence or whether protective structures might exist. The frontier extends into medicine as well. Clinical studies test whether different anesthetics produce distinct patterns of brain disruption, consistent with quantum or classical mechanisms. Others explore whether psychiatric treatments, electroconvulsive therapy, transcranial magnetic stimulation, even psychedelics, might act in part by modulating coherence. If so, the implications for therapy are immense. Treatments could be tuned not only to neurotransmitters, but to quantum rhythms, restoring harmony where it falters. Skeptics remain vigilant. They remind us that extraordinary claims require extraordinary evidence. Many experimental results cited by supporters are weak, contested, or unreplicated. Artifacts lurk in every corner: electrical noise, thermal fluctuations, instrumentation limits. The burden of proof is high, and the frontier is filled with false dawns. But science thrives in persistence, and the persistence here is palpable. Even mainstream projects, unconcerned with consciousness, feed the debate. Photosynthesis experiments reveal coherence lasting longer than expected. Avian magnetoreception studies strengthen the case for entanglement in biology. Enzyme tunneling research shows quantum mechanics woven into metabolism. Each of these is not proof of OR, but proof that life can, under some conditions, preserve quantum order. They shift the burden of skepticism. If leaves and birds and enzymes can, why not brains? Future experiments loom on the horizon. One proposal is to entangle biological samples with laboratory qubits, testing whether biological systems can sustain non-classical correlations. Another is to track coherence in anesthetized animals, comparing wakefulness, dreaming, and silence. Still another imagines implanting quantum sensors directly into neurons, mapping oscillations at the molecular scale. These frontiers demand not only technology, but courage. The courage to ask if the most intimate mystery of existence can be measured. Beyond the lab, the experiments carry philosophical weight. If coherence is found, if quantum sparks in microtubules prove real, then consciousness is not just a byproduct of neurons, but a window into the foundations of physics. The mind would be a bridge between biology and the universe, collapsing wave functions into moments of self. If coherence is not found, if experiments fail again and again, then OR may fade into history. Yet even then, the pursuit will not be wasted. For in chasing this vision, we will have mapped the brain with unprecedented precision, built tools of astonishing sensitivity, and deepened our grasp of both biology and physics. Picture the frontier as a horizon glowing with first light. Instruments glint like ship's sails. Researchers stand on the shore, scanning the waves for signals, faint and fleeting. Some believe the treasure is there, hidden beyond the noise. Others believe the ocean is empty, that the signals will never come. But all agree on one truth: the voyage must be made, for the question is too profound to leave unasked. The frontiers of experiment are not yet conclusive. They are whispers, half-formed data, fragile hints. But in those whispers lies possibility, and in possibility lies the hope that one day we will know not only how neurons fire, not only how networks integrate, but how awareness itself burns bright within the brain. Until then, we remain poised on the edge of discovery, listening for signals, reaching toward the unknown. The journey has carried us across the most daring landscapes of science and imagination, through Penrose's impossible equations, into the hollow lattices of microtubules, through the hurricanes of decoherence, the green light of photosynthesis, the silent fog of anesthesia, and the vast mirrors of the cosmos. We have followed consciousness as it fractured, expanded, and flickered, always just beyond the reach of certainty. Now, at the edge of the journey, it is time to slow, to let the questions soften into a quieter rhythm, to return gently from the stars and the atoms back to the simple act of being. Close your eyes, if you will, and notice the breath moving in your body. Inhale. Air enters, carrying oxygen that binds to blood, flowing to cells, fueling the dance of neurons. Exhale. Carbon dioxide leaves, the soft trace of metabolism returning to the atmosphere. This quiet rhythm is the backdrop of consciousness, a tide that has carried you since birth. You need no theory to feel it. You need no physics to know that awareness rides upon it. Science can take us far. It can measure oscillations, track networks, test coherence, and build models of mind. It can imagine consciousness as information, as collapse, as cascade. It can propose that awareness is a spark of quantum order, or a broadcast of classical networks, or a fundamental feature of the universe itself. And yet, none of these theories capture the immediacy of now, the felt sense of being alive in this moment, hearing these words. That immediacy is the one experiment you cannot escape, the only evidence every conscious being shares. In the end, perhaps the purpose of theories is not to solve consciousness, but to deepen our wonder at it. Whether the mind is woven of microtubule harmonies or neuronal networks, whether it is born of collapse or integration, its presence remains a gift. You open your eyes each morn, and the world arrives with color, sound, and memory. You dream each night, and the universe remakes itself from fragments of thought. You ask questions, you imagine, you love, you fear. None of this requires proof to be real to you. Consciousness is the ground on which all questions stand. The quantum mind theory, even if unproven, leaves us with a luminous possibility that in every flicker of thought, the universe is resolving itself, collapsing probabilities into presence, that your awareness is not only personal but cosmic, a ripple in the same ocean of possibility that birthed galaxies. To live with this vision is to live with reverence, to see each moment as a thread connecting mind to matter, self to cosmos. But the classical guardians remind us of another truth, that awareness may be no less wondrous if it arises from the complexity of neurons alone. To weave memories from firing patterns, to paint the self from networks of integration, is already miraculous. Even without quantum sparks, the brain is a cathedral of electricity, every moment a stained glass window illuminated by experience. Whether quantum or classical, emergent or fundamental, awareness carries you through your life. It is here, now, in the weight of your body on the bed or chair, in the warmth of your breath, in the quiet of the room. The theories may inspire awe, but the truth of consciousness is always already with you. So let the questions recede like a tide. Let the noise of debate soften into silence. For tonight, you need not solve the mystery. You need only rest within it. Feel the vastness of the cosmos fold back into the rhythm of your own body. Feel the complexity of neurons, the fragility of quanta, the architecture of time, all dissolving into a single simplicity. You are here, you are aware, and that is enough. The journey through the quantum mind has been a journey through wonder. We have stood at the crossroads of physics and philosophy, peered into microscopes and telescopes, traced the fractures of self and the mirrors of the cosmos. And now we return, gently, to where it all began, not in equations or experiments, but in the quiet certainty that awareness itself is the greatest mystery, the softest truth, the most intimate of miracles. Allow the breath to carry you downward, into calm. Allow the theories to dissolve like dreams at dawn. Allow the mystery to cradle you, not as a puzzle to be solved, but as a lullaby to be heard. For the universe, in all its strangeness, has chosen this moment, this awareness, this life. And that is wondrous enough. Sleep now, if you wish, with the thought that the cosmos gazes through you as you gaze through it. Sleep with the sense that every breath is part of a rhythm older than stars. Sleep with the comfort that whether consciousness is quantum or classical, fragile or eternal, it is yours, and it is beautiful.